Hello everyone. Thanks very much for joining. Let's put some music on, if that's worked. Hi guys, thanks very much for coming to the stream today. Welcome, a very warm welcome to Journal Club. This Tuesday afternoon where I am. It may be a different time, it may be a different day for you. Thanks for coming. So, this is Journal Club, and my name is Robert Palgrave, the host of Journal Club. For now, I'll explain a little bit before we get started about what Journal Club is, what Journal Club's for, how you can interact with Journal Club. So, for those of you who don't know, a Journal Club is a regular meeting where people can discuss academic journal articles. So journal articles, papers, the way that academics communicate with each other, scientists especially, the way that scientists communicate with each other is through journal articles. So in a Journal Club we look at scientific articles and discuss them. So this is the kind of meeting that goes on in many research groups, universities, research institutions, even companies. Anyone who kind of does research can benefit from a Journal Club. So normally, of course, they're not on Twitch. In fact, there's not very many on Twitch. I have been doing some background research on this. There are a few others, not many in English actually. There's a few channels that do an occasional Journal Club, but I don't think there's any that do only Journal Club. So that is the niche that is trying to be filled here. So the point of a Journal Club today, like every day, we're going to be discussing a paper. And I try to choose papers, so far I have only chosen papers that are open access. So open access means that anybody with an internet connection can access the article. So some articles are not open access, you have to pay money, sometimes quite a lot of money, to read the article, even if you wrote the article yourself, which seems kind of ironic. Maybe one day we'll have a stream about publishing ethics, or the publishing system and all the things that are wrong with it, but I think that's not going to be this stream. Maybe in future. But let me know if you want to hear that, because I could probably go on for quite a long time about all the things wrong with the publishing system. But anyway, I can't say it too loudly. There might be some editors watching. Probably not. They're far too busy. They've got too many important things to do. They wouldn't be wasting their time here. Anyway, so today, like always, we are going to be reviewing a paper. And if you want to find out what that paper is and maybe read along, there is a chat command that you might be very interested in. So that chat command is !paper. And I'm going to type that for myself right now in the chat. And when you do that, the chatbot will reply with a link to the open access paper that we're going to be discussing today. So if you want to read along, you can do that. You can click the link and you can follow along. But of course, the text is going to be on the screen here as well. So whatever works for you. You might want to stay here and watch. You might want to just listen and look up the article yourself and look at it on your own reader. Especially in case it's not good enough resolution to see everything. You might want to zoom in on certain details that I'm not zooming in on. So in that case, it might be handy to have the article open as well. Anyway, so without further ado, shall we have a look at the article today? So the article today is called "Do Electron Distributions with Orbital Degree of Freedom Exhibit Anisotropy?" And this is an article in Journal called Materials Today, which is published by the Royal Society of Chemistry. Materials Advances. Good reading skills already. Published by the Royal Society of Chemistry. Pretty recently. I think it's in the latest edition of Materials Advances, not Materials Today. Don't go looking for that. And this is by a group of researchers, mostly in Japan, I think. They're using some large-scale facilities, some synchrotron facilities in Japan, which we'll talk about. And this is the latest in their series of papers, where really they are, I always say, pioneering a new way of understanding electrons in solids. So for someone whose background is in chemistry, which is mine, and materials, the electrons are kind of what chemistry is. The chemistry, you could kind of say, is the one description of chemistry is the science of electrons, because chemical processes are pretty much exchange, movement, some kind of processes that happen to electrons. Electrons are what stick atoms together. Electrons are what or changing distribution of electrons is what causes chemical reactions to happen. So pretty important. We have lots and lots of ways of understanding what electrons are doing in molecules, in solids, in just atoms on their own. So of course our understanding, our modern understanding of how electrons behave comes from the developments at the beginning of the 20th century, quantum mechanics, quantum theory, where the idea of what an electron is or what a particle is was kind of completely upended and changed. But we don't want to do too much of a history lesson. Bringing it up to the modern day, there's lots of ways to kind of understand electrons in materials. So we can do calculations with supercomputers, things like density functional theory, which will calculate to a very high degree of precision where the electrons are, what energy the electrons have within a molecule or within a solid, a non-molecular solid maybe. So we can do it computationally. There's also lots of experiments we can do, lots of kinds of spectroscopy we can do to understand electrons. And the reason spectroscopy is so good at investigating electrons is because electrons interact very strongly with photons, so with light. So electrons interact with light. In fact, if you look around you in a room where you are right now, almost all of the colours you can see, I guess not counting your, well actually even counting your whatever display screen you're watching this on, but any non-display screen objects you can see around you that have a colour, that colour is almost certainly due to electron, the material is absorbing light because of electron transitions within that material. So dye molecules, the reason dyes are coloured is because the electrons can jump to different energy levels and absorb light, and so they look, to us they look coloured. When they absorb part of the visible light, then they look coloured. So electrons interact very strongly with light, so there's lots of different ways we can kind of understand what electrons are. We can do different kinds of spectroscopy. We do things like photoemission spectroscopy, which kind of detects electrons directly, or we can do just visible light spectroscopy, like I just mentioned, so looking at the colour of something. You can do that a little bit more high-tech version of looking at the colour of something with absorption spectroscopy or reflectance spectroscopy, and that can tell you, you know, if you see a peak in your spectrum, that could be due to an electron moving between energy levels, and now you know the energy difference between those two levels because that's the energy of the photons that are absorbed. So there's lots of different ways, but I think this is what we're going to be talking about today. I think this is a really smart, exciting, potentially, well, it's a very smart method, I think, for understanding electrons in solids. It might be that it's just too difficult to apply to many systems, or the equipment you need to do it is just too difficult or too kind of restrictive on how much access you can get to that equipment. So it might not become you know, a technique which is used by everyone around the world, but as a methodology I think it looks really smart. So we're going to do a little bit of a background of that, and then we'll go on to the paper. So what is this methodology about? Well, we'll have a little look at the abstract. So the abstract here at the beginning of the article. Doesn't want to highlight. No, it wants to highlight everything. Okay, let's go to let's grab the highlighter. Okay, let's have a little look at the abstract. So first sentence is not really relevant to the methodology. Orbital degrees of freedom appear in partially filled degenerate orbitals and are responsible for a variety, highlighting is not working for me at the moment, a variety of physical properties. I'm going to go to the pen. The pen is mightier than the highlighter. A variety of physical properties. Okay, that's true. We're going to come on to that later on. I think that's not really to do with the methodology. Although many methods for directly observing orbital states in ordered states have been proposed, it is difficult to determine degenerate orbital states directly. Okay, we'll define what that means later on. We found that high precision diffraction data obtained by synchrotron radiation X-rays can be used to observe only the valence electron density distribution with minimal analytical bias. The results attained using this method, and then they go on to talk about that. But this is the methodology. I'm going to rub that out because I basically drew all over everything. This is the methodology that I'm talking about. Precision diffraction data obtained by synchrotron radiation X-rays can be used to observe only the valence electron density distribution with minimal analytical bias. Okay, so we'll talk a little bit about diffraction. Many of you may be familiar with diffraction. Many of you may not be. So diffraction, especially X-ray diffraction, was really, we're going back to history lesson again, but it was really a revolutionary moment, I would say, in science. So there's lots of really important moments of science in the 20th century. We talked about quantum mechanics. A lot of it comes from kind of the physics point of view, but actually I think X-ray diffraction development, discovery, and then the understanding of X-ray diffraction is kind of right up there. Because X-ray diffraction, what that allowed us to do is to really see into the atomic world for the first time. So we could, using X-ray diffraction, actually measure things on the atomic scale. How big is an atom? How far away is the next atom from that atom? What's the overall arrangement of atoms in a particular material? And before X-ray diffraction, you just couldn't do that. There were lots of kind of indirect ways that you could try to get an idea of how the electrons are, how the atoms are arranged. Sorry, but nothing told you kind of directly and unambiguously the positions the atoms are in. So X-ray diffraction, or XRD, discovered in 1912 in Germany, but really explained most fully by the English scientists, or the father-son team of Lawrence and Henry Bragg. In the years afterwards. That kind of is a big moment, especially for chemistry, because we can now actually measure molecules. We can see molecules, or we can understand the arrangement of atoms in a solid. That was kind of unprecedented before. Also for physics, also a lot of geology, and even up to the current day, it's used in biology to look at proteins, to look at huge molecules, which the originators of the technique would never have believed you could do. So the X-ray diffraction is a very well established technique, and what X-ray diffraction does, it gives us, it only works on crystalline materials. So it works on materials which have what's called translational symmetry, or they're ordered materials. So the atoms form a very neat pattern. When we shine X-rays onto those atoms, just like if you shine light onto what's called a diffraction grating. Yeah? So if you shine light onto a diffraction grating, you get a diffraction pattern. If you shine X-rays, which is just the kind of light, onto a regular arrangement of atoms, then you get a diffraction pattern. You can go from that diffraction pattern backwards. If you're good enough with the maths and you understand what you're doing well enough, you can go from, with a few assumptions, you can go from that diffraction pattern backwards to work out what the structure was, so the original atomic structure. That in a nutshell is what XRD does. It's an unbelievably important technique in a huge range of sciences, especially material science, which is what I work in, especially solid state chemistry, but like I said, lots of other things as well. But as I said before, X-ray diffraction uses light, uses X-rays. X-rays interact most strongly, if you think of your atoms making up your compound. The X-rays interact most strongly with the electrons. So photons interact very strongly with electrons. They interact very weakly with the nucleus. So protons and neutrons and nucleus, they don't really have too much interaction with, but X-rays interact really strongly with the electrons. So when we understand the positions of atoms in a crystal using X-ray diffraction, what we're really doing is understanding where the electrons are in the crystal. And of course where the electrons are, or where most of the electrons are, is of course where the atoms are. That makes a lot of sense. So let's think about the structure of an atom. An atom of course has got a nucleus in the middle, lots of electrons around the outside, and especially heavier atoms, most of their electrons are what we call core electrons. So they're just kind of hanging out inside the atom, not really doing anything. They're very strongly attracted to the nucleus. They can't escape. They're so strongly attracted to the nucleus, you know, they can't really go and interact with any other atoms because they can't move away from the nucleus. Yeah, they're held very, very tightly. Those are called core electrons, and from a chemist's point of view, they kind of don't really do anything. Yeah, they're just there. Obviously, they have charge. They contribute to the overall charge of the atom, but chemistry-wise, they're kind of dull. Yeah, they don't really do anything. The other kinds of electrons, the ones that we're much more excited about as chemists, are the outermost electrons. So these are called the valence electrons. So the valence electrons are the ones right on the outside. Now, they are the furthest away from the nucleus, so they're held less tightly by the nucleus compared to the core electrons. So they can interact with other atoms, with other nearby atoms, and in fact that's what they really like doing. So they like interacting with other atoms. They form they're what form chemical bonds. They're what stick atoms together. Yeah, they're the reason that any of this is here, because if atoms didn't stick together, then the universe, I think, would be a less interesting place. We can probably agree. So the valence electrons are on the outside, but for most atoms, there's far more core electrons than there are valence electrons. So for most atoms, you know, the heavier you get, the more core electrons you have, and the fewer, well, you have roughly the same number of valence electrons, but as a proportion, the number of valence electrons is kind of lower. So when we're doing X-ray diffraction, most of what we see is the core electrons. Most of what we see is these kind of chemically dead electrons, you know, living out their boring existence in the center of an atom, literally never doing anything, pretty much, unless, you know, something exciting like an X-ray comes along, then they've got a chance of some excitement. They might even get ionized. You know, that would be big news if they could actually leave the atom and see the rest of the universe. But anyway, we're getting into photo emission, which is not the topic for today. So what XRD normally looks at is the core. What most of what we see with XRD, X-ray diffraction, comes from diffraction of the core electrons. But of course, the valence electrons are still electrons, yeah, so they're still going to diffract X-rays, or still going to interact with X-rays, and it's part of the diffraction that you get from X-rays is to do with, it's attributable to the valence electron. But because the valence electrons are so few in number, and because they're so spread out and not all stuck together in one place, it's normally much harder to kind of understand what the valence electrons are doing. And you can just, if all you care about is the atomic positions, which is mostly what we're interested in X-ray diffraction, the core electrons will do the job. Yeah, they'll do the job. They will identify where the atoms are. Yeah, because there's so many of them. Anyway, what these guys have been doing, and I'm actually going to skip back to their original, what I call original paper. Let's go up to the beginning. This is an older paper from the same group, or from mostly the same authors. But this paper just lays out. My line drawing is terrible today. They set out a little bit in a little bit more detail what the actual methodology is. So I'm going to quickly skip to this paper. We're not going to spend too much time on it. I haven't got a bot to show you the link, I'm afraid. I should do that. I should have an exclamation mark paper 2. That's probably a good idea. But I haven't done that because I only just thought of it. So anyway, you guys, if you're desperate to see this article, maybe I'll tweet it afterwards, or you can. I'll definitely forget to do that. So just you know, type in this title into Google and you'll find it. Anyway, what these guys do in this paper is they separate out the contribution to the diffraction from the core electrons. Remember, the chemically dead, boring as hell electrons in the middle, and the valence electrons. Yay, exciting chemistry. They managed to separate out those two components from the diffraction data, and then they subtract away the core electrons the contribution of the core electrons, and what they're left with is a distribution of the valence electrons. So they're left with a three-dimensional real space distribution of the valence electrons, showing you where those electrons are. That's pretty exciting. I'm going to read a little bit from the methodology, because I like the way they set this out. Actually, we're not going to go through all the mathsy bits. I'm most pleased to hear that because that would be too difficult for me. We may touch on a few things that I'm possibly understand or not. So okay, maybe we'll scoot up. Oh no, actually we need to be. Oh no, this is where we need to be. Okay. Okay, let's skip to here. So all right, let's see where they did the experiments. They did the experiments on this beamline, which is a major synchrotron facility in Japan called Spring 8. This is one of the leading synchrotrons in the world. The thing about a synchrotron is that it has incredibly intense beams of X-rays. So far more intense than what was originally used to do X-ray diffraction, far more intense than what's used in most labs around the world. These are basically particle accelerators which have the sole purpose of spitting out almost unbelievably bright X-rays, brighter than the sun by some ways you can measure. I think when every time they turn on a new synchrotron, the press release always says that when this synchrotron was turned on, it became the brightest object in the solar system, including the sun. Yeah, so by some definitions of brightness, I'm not a synchrotron person, there's definitely proper definitions of brightness. By some definitions of brightness, the synchrotrons are brighter than the sun, which is kind of quite impressive, you know, for a man-made thing. The sun is kind of a pretty big object, and that we are outshining it with these synchrotrons. So I don't know whether Spring 8 is the brightest synchrotron in the world. I'm sure it was at some stage. It may well not be anymore. If you know, you can write it in the chat. There's a chat box right there if anyone knows, or just wants to guess. This is where they did it, but let's have a little look at the maths down here. So the diffraction intensity obtained from the XID experiment can be described as a Fourier transform of the ED. ED is electron density. Okay, again, I'm doing a terrible job drawing over everything. Let's make this slightly bigger so you can see. So the diffraction intensity obtained from the XID experiment can be described as a Fourier transform of the electron density. So Fourier transform is a mathematical method that allows you to move, in this case, from information in a spatial domain into information in a spatial frequency domain. We're not going to go into exactly how that all works, mostly because I don't really understand it. It's just kind of magic. Yeah, so you do Fourier transform, and you can change your, for example, if you have a real space picture of a regular arrangement of atoms, for example, or regular arrangement of anything. People do this when there's someone tweets out pictures of tile patterns. I think probably kind of medieval Islamic tile patterns, maybe from Andalusia, where they had, you know, very complex geometry, very kind of intricate patterns, and they then tweet that along with the Fourier transform. So Fourier transform is a way you can turn a real space image or an actual picture with a regular and ordered arrangement of things in it. Objects, could be atoms, could be tiles, could be anything, could be cats, and you transform that into a depiction of the spatial frequency. So the spatial frequency is in a given distance, how many times do I have this thing? Yeah, so if I, you know, in 1 meter, in 1 nanometer, in 1 angstrom, doesn't matter. How many of these objects do I have per meter? You know, so if you had, I'm trying to think of a good analogy. If you had an American football field, and pretend in some alternate universe, America was in a metric system. So pretend America is in a metric system, but inexplainably they still play American football. I think these things can't coexist. I think that's the only reason they're not having the metric system. because American football just would, I don't know, it just seems incompatible. But anyway, so imagine an American football field was 100 meters long instead of however long it is, probably 100 yards, I don't know. And you know, it has that grid pattern, you know, so how many of those grid lines are there per 100 meters per the length of the field? Well, I think there's 10 of them. I think there are 10-meter lines. I don't even know. I shouldn't have done an analogy about American football that I don't really know anything about. But imagine that, if you can, how many lines are there per 100 meters? There's 10 of them. So the spatial frequency is 10 per 100 meters. Yeah, or 0.1 per meter, if you want to convert it into meters, or you know, you can go down into nanometers or angstroms if you want. So a Fourier transform will convert the real space arrangement of objects into a spatial frequency domain, a spatial frequency depiction of the objects. I'm not gonna. American football is a bad choice. There's probably a way better analogy, but I can't think of it at the moment. Anyway. Here's an equation saying that. So the diffracting intensity. So the intensity is a thing you measure, yeah? So you're measuring a particular angle or a particular scattering vector, as they call it here. You're measuring how bright are the X-rays which come off your material. So how bright are these X-rays? That's what you're measuring. So this is a real thing that you can measure in actual real life, yeah? And it's related by this equation to this thing, and this thing is the electron density. So how many electrons are in a particular place. So that's pretty cool, yeah? You can go from something you can measure in real life to something that tells you about the electron density within the solid or within the material at a particular place. That's kind of what we want to know. So that's everybody knows this who does X-ray diffraction, that's kind of the thing that you are measuring. What they then go on let's find the, there we go, okay. The calculation of the electron density, this is a good part of the paper. I thought this worked really well because they set out kind of the problems with the methodology they're trying to accomplish, and then they show how they solve all of those problems. So I thought that worked quite well. The calculation of electron density generally has 3 problems. One, to extract the VED. So VED is the valence electron density. So remember, the valence electrons, the outermost electrons, they're the exciting electrons, they're the party electrons, they're the ones which are actually doing chemistry and not just kind of sitting in their little dungeon in the middle of the atom like the core electrons. Yeah, they're boring. Physicists like them, no one else likes them. So to extract the valence electron density, and that's a new thing here. With anisotropic information, a sufficiently wide dynamic range of intensity is required. So what that means is you need to be able to see very, very tiny changes in a huge signal. Yeah, so you're going to have a large amount of intensity from your synchrotron, and you need to be able to detect very, very small changes in that, or you know, or changes over a very wide range of intensity is actually a better way to say it, isn't it? Or better way and actually correct way of saying it. So this is the first problem. We need sufficiently wide dynamic range of intensity. The second one is that this is called the observed structure factor. So I kind of skipped over the bit about structure factors, but structure factor, okay, the intensity is also proportional, as well as being proportional to this, is also proportional to the structure factor, which is this FOBS thing, or the observed structure factor. Well, yeah, so the absolute value of the experimentally observed crystal structure factor. There you go. We'll talk about a little bit what the crystal structure factor is. Maybe I don't want to go into too much into that. It might get a little too involved. But anyway, this structure factor is obtained from experimental diffraction intensities because the relationship of this relationship, which is shown above, between the intensity and the structure factor. But note, we have the modulus of the structure factor squared. Okay, so in this case, the modulus of the structure factor does not include information of the phase term, because the phase term kind of disappears when you take the modulus. And unfortunately, the phase term is necessary for calculation of the electron density. So what do we mean by phase? So light has got both intensity. So if you measure a beam of light, it's got intensity. So that's how strong, how many photons there are. But it also has phase. So if you imagine light as a wave, it's what phase that wave is in. So how do those waves line up with something else? So the phase has to be relative to something, but how does a phase line up with, how do those waves line up with something else? That's what the phase is. Now when we detect the photons, when we measure the photons with a detector, we can detect the intensity, we can see how many there are, but what we can't do is measure the phase. And that's a big problem, because as you saw, the equation for the electron density up here relies on knowing what the phase is. It relies on this P term. Yeah, this P term here, phase. So if we don't know what phase is, we can't measure what the phase is, then we can't actually calculate mathematically the electron density. So that seems to be a bit of a problem. They're going to comment on how they solve. There's actually lots of ways to not solve this problem, but to overcome this problem. This is called the phase problem in XID. There's lots of ways to overcome the phase problem, which you can read about if you type in phase problem XID. There's a nice Wikipedia article, I think. Problem number 3, because the number of observations is finite, the mathematical truncation effect seriously affects the electron density distribution. Okay, we're probably not going to go into that, mostly because I don't really understand it. But if anyone does understand it in the chat, you know, I would be very, very happy to hear about it. But here they set out, which I think is a very effective way of writing. Here they set out how they solve all those problems. So with regard to 1, so remember 1 is the fact that really there aren't many valence electrons compared to the core electrons. So let's have a look. The relationship between a number of focused electrons. So by focused electrons, I think what they mean here, it's the only time the phrase focused electrons appears in a paper. I think what they mean is the valence electrons. So they're saying they're focusing on the valence electrons. Yeah? The relationship between the number of focused electrons and the number of electrons in a unit cell is important. Yeah, sure. In the case of quasi one-dimensional molecular conductor, this is an organic-y thing that they're talking about. A 3/4 filled system, because X minus is a monovalent anion, such as these things. Okay, blah blah blah. The number of electrons in this unit cell is approximately 350. Okay, so they're interested in this particular organic semiconductor thing, which I think they must show a picture of, surely. Do they show a picture of it? Maybe they don't. They've got some diamond later on. Anyway, the number of electrons in a unit cell is about 350. To estimate the amount of charge transfer in one of these dimers, a dynamic range that can extract. Okay, so 1 electron charge transfer. So basically, they need to be able to see 1 electron out of a background of 350 electrons. So it's 350 electrons in total. One of those is the what they call a focused electron, or the electron that they are interested in for their particular problem. So it's not even all of the valence electrons. It's not like they want to see all of the valence electrons. They want to see one particular valence electron in one particular part of this dimer, this molecule, in order to see it. So you're looking to see a change of one thing in 350 things, but one thing in 350 things. So the dynamic range that you need to accurately extract that is 1 squared divided by 350 squared, which is about 10 to the minus 5 of the maximum measured intensity. So you need to be able to see changes of 10 to the minus 5 compared to the maximum intensity. So 1 out of 1 part in 100,000. You need to be able to see that difference in your signal. So that's technologically challenging, but this is what they can do at the synchrotron. This is why they do this experiment at Spring 8. This is why they do it at the synchrotron, because the 10 to minus 5 signal information should be observed with a sufficient signal to noise ratio. Okay, so there we go. You can do that at Spring 8 on that diffraction beamline. You can see that kind of signal to noise. 10 to minus 5 is no problem for that. This requirement is sufficiently filled using the current synchrotron radiation facility, in which a dynamic range of 10 to the 6 is guaranteed. Guaranteed! Guaranteed! You can put that one in the bank. So yeah, they can do that at the synchrotron. With regard to 2, they're going to tell you how they do the phase term, but basically what they do, as far as I understand it, it's kind of like, again, I'm not a crystallographer. If there's crystallographers in the chat, you can correct me about the incorrect things I'm saying. I think this is roughly right. They're using what's called direct methods. So they they kind of, well, in this case they know what the structure is. They're only looking at structure of known materials, so they know what the structure is. They can calculate using the kind of theoretical structure factor, or the calculated structure factor here. Yeah, they can calculate what the phase term would be, and then assume that that is then correct, and use that phase term for the calculation you need to do. The smart bit down here, I think, is this bit. So I think this is kind of the key to their whole methodology. So it turns out that the atomic scattering factor, so the scattering factor of each individual atom, yeah, so the scattering factor of the individual atom will be contributed to by all of the electrons in the atom, so the core and the valence, but it has this angular dependence here. So they've got a sine theta term down here. So an angular dependence, the angle of the diffraction, determines how much the valence orbitals actually contribute to the scattering factor, and you can see that they only do that at very low angle, very small angles. So the valence electrons here are the kind of orange line, which for some reason I'm colouring in blue, which just makes everything far more confusing. Let me rub that out. The orange line, which I don't need to point out to you because you can see it, the orange line here are the valence contribution. You can see it only really makes it's only a big deal at low scattering angle, yeah, very low angle. When you go to high angle, it's basically the total scattering factor, which is this black thing, is basically only determined by the core orbitals. So if you calculate so if you only look at larger angle scattering, your valence electrons are basically not involved at all. Your valence electrons aren't involved, don't contribute to the scattering factor of the atoms, and so they don't contribute to the overall structure factor at all, which is exactly what they then exploit to take the let's just see exactly what they've done. Meanwhile, in equation 7, which is this equation up here, the inverse Fourier transform is performed on the term obtained by subtracting the core electron contribution from the observed structure factor, which contains the contribution of all electrons, because most of the contribution of the remaining valence scattering, the scattering factor of the valence electrons, exists only in this very low angle region down here where we said before. The valence electron diffraction can be extracted with little truncation effect of the Fourier synthesis by the CDFS. That's the name of this technique, which I've forgotten what it's called. What does CDFS stand for? It's the name of this methodology, which I'm going to find probably in a minute. There you go. Core differential Fourier synthesis. Core differential Fourier synthesis. Okay, so that's how they overcome this truncation problem. To be honest, I didn't really understand the truncation problem in the first place, but I'm glad they were able to overcome it. Okay, so they can subtract away the calculated structure factor based only on the core electrons from the observed structure factor based on all electrons, and what they're left with then is just the valence electron density. In this paper, which is not the paper we're looking at, if you have come in and you're interested in the paper we are going to be looking at, you can type !paper in the chat, and you will get a link to the actual paper. I'll briefly mention here, in the rest of this original paper, which is just setting out the methodology, they do diamond, which is kind of nice because diamond was one of the first structures solved originally by X-ray diffraction, and they show they map the valence electron distribution of the valence electrons in diamond. That's quite nice. I think they do some other compounds as well. Oh, they also do C60, so they do Fullerene. That's pretty nice, isn't it? So you look at the valence electrons in Fullerene, you can see them all spread out along the bonds here with none of them in the middle, and a nice little cross section throughout the molecule there. We can see where the valence electrons are bonding these. I mean, look how delocalized they are. In fact, even go to diamond. That's not. What is this one? Valence electron density, surface spot sectional view. What's the difference between these ones? Oh, that's a total electron density. So C and D is a total electron density. This is a valence electron density of diamond. So the cool thing about diamond is really the valence electrons are very, very delocalized, so they're really spread throughout the whole structure. So kind of the naive approach to understanding bonding in diamond is just that the electrons are trapped between the carbon atoms in these sigma bonds and these localized bonds, and that's why carbon doesn't conduct electricity, because the electrons can't move. That's why it's an excellent insulator, as opposed to graphite. And I know this isn't graphite, but it's a bit like graphite because it has sp2 carbon, so it has delocalized electrons in a ring. But actually, if you look at the electrons here compared to the electrons here, they're all, you know, these ones are joined up to here, joined up to here. The diamond electrons are actually pretty delocalized. The reason that the reason that diamond is not a good conductor is because all of the valence electrons are completely filled. All of the electrons, the valence orbitals are completely filled. So even though the electrons are moving through the structure, there's always an equal number moving left and an equal number moving right. So actually there's no way you can get a net movement of electrons in diamond. The electrons themselves are actually pretty mobile, and if you put some extra electrons in or take some electrons away from diamond, you can actually get something that's pretty conducting. And this is nice to show that you know, the electrons in diamond are not localized. They can go everywhere. Yeah, they can kind of move all through the structure, which is good. Anyway, I think 45 minutes in, maybe we should talk about the actual paper. If you want to get the paper, paper in the chat, and you will be furnished with a link. So we talked a little bit about their method. They can use this diffraction method, using the idea of having very high intensity synchrotron radiation, and a few of those kind of clever ways to mitigate some of the problems that they set out in their last paper, points 1, 2, 3, and they can use that to look at the valence electron density. So I'm not going to really go through that much more. Let's look at what they actually did with it in this paper. So they looked at a particular material. Well, let's look at a little bit of the. Actually, you know what? I think we won't really read the introduction. I'm just going to go straight to the meaty parts. We're going to look at this material that they are exploring. So this is the material that they are exploring. So it is iron vanadium oxide, so FeV2O4 is the material they're looking at. So let's see what they say about this. The configuration of, I'm going to try highlighting again. Highlighting wasn't working for me before, but I'm going to try. The configuration of the partially occupied d orbitals leads to peculiar magnetic and electronic transitions, such as the Fourier transition of Fe3O4. So this is a very famous metal insulated transition in Fe3O4, which is magnetite. So this is to do with the kind of subtle changes in the energy levels of electrons. In this study, we focus on the orbital state of the vanadium spinel oxide FeV2O4. Okay, so FeV2O4 is kind of like Fe3O4, except we've replaced two of the ions with the Fe with vanadium. Yeah, it still has the same structure, has an isomorphous structure as magnetite in the high temperature phase, at least anyway. So in this system, despite lack of charge degrees of freedom due to the Mott insulator, that means the electrons can't move around because there's too much electron-electron repulsion. Both electronic correlations and geometric frustrations are present, resulting in an interplay between different degrees of freedom, such as spin, orbital, and lattice, which leads to 3 successive phase transitions with decreasing temperature. Okay, so this is an interesting material that understanding the different phases, the different structures that it forms, the different phase transitions it goes through, can tell us a lot about how the competing factors that are causing the structure as a whole, or the electrons, to want to occupy particular arrangements. What they're looking at really here is just the high temperature polymorph of this. Now let's see if I can grab up Vesta. Let's see if Vesta is going to emerge from the. Are you going to emerge, Vesta? Vesta is here. Vesta is here, and I'm going to hopefully have the. Yeah. Okay. So here, let's load up these two structures for you guys. So this first one here, this is Fe3O4. These are magnetite. So all of the kind of orangey golden colour ions are Fe, and the red spheres are oxygen. Okay, so I'm going to change the style here to polyhedral, and I'm going to get rid of the bonds, because who likes, I think bonds kind of like that. You may be able to see if I rotate these, and actually, you know what I'm going to do? I'm going to subtly change the colour of some of them. Let's do, that's not that subtle, but anyway. We have different kinds of polyhedra here. So polyhedra, I think we discussed in a stream before, it's just a way to understand the arrangement of ions around a metal centre. So here, for example, you have a tetrahedron, you have an ion in the middle, and it's got these 4 oxygens around it in what's called a tetrahedron. The oxygens form the points of a tetrahedron. So this polyhedron is filled in. Obviously it's not really there, things that are really there are the atoms, but it helps us to kind of understand the arrangements. So we have 2 different kinds of polyhedra in this spinel structure, very famous solid state structure. We have these tetrahedral ions, and we have these ones which are still this kind of golden colour, and a slightly more yellow colour. We now have these octahedral ions, yeah, these octahedral points here. So they're both Fe, they're both the iron, the metal at the centre is always iron, but they form these different arrangements. Now let's have a look at this is magnetite. This is not the material they're looking at, but this is the material they're looking at. I'm just going to try to quickly show it in a similar way. Have I messed something up here? Have I? Oh, hang on. I opened the wrong one. Hang on. Let me try and find the right one. There we go. Here's the compound that they were looking at. All right. So we'll go back to polyhedral. We'll get rid of the bonds. So here we have the actual compound that they're looking at, this FeV2O4. So they've replaced, you can see, if we go to the polyhedra, the vanadium ions are on the octahedral site, so they are the red sites here, and the iron still remains on the tetrahedral sites here. So from this depiction, it looks kind of similar. Let me close this because I didn't mean to have this open. No, I don't want to say changes. It looks pretty similar to what we have here, yeah. So if I kind of line them up in the same way, flick between them, it looks pretty similar. We have almost the same structure. We have octahedral sites and tetrahedral sites, but in this case, the metals are separated out. So the iron only goes on the tetrahedral site, and the vanadium only goes on the octahedral site. You'll also see, if you look very closely, the octahedral sites here are slightly distorted. They're not the more regular octahedron that you get in Fe3O4, but in FeV2O4 you have a slight distortion of the octahedron. So we'll talk about why that is in a minute. You can kind of see it here. I think some of these look not quite regular octahedron. In fact, it's probably easier to see if I take off the polyhedra. Yeah. In fact, if I remove the metals entirely, you can see the way that the oxygens line up is, let's get rid of the polyhedra, let's go to atoms, get rid of the metals. Yeah, you can see the way that oxygens line up is slightly different between the two. You see, as I flick between them, they kind of move. So this is the FeV2O4, this is the Fe3O4. So they're in slightly different positions, they're slightly more distorted in this one. Anyway, let's get back to it. Let's get back to the paper. So blah 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 blah. So in Fe2O4, because the formal charges of iron, oh, you can't see, sorry, let me scroll down, apologies. In Fe2O4, because the formal charges of iron and vanadium are +2 and +3, the electron configurations are 3d6, 3d2 respectively. So that's just from knowing the group number of the periodic table. Iron's in group 8, so iron with +2 charges has 60 electrons, 6 valence electrons. Vanadium is in group 5. It's in a +3 oxidation state, so it has 2 valence electrons remaining. Remember, vanadium's in group 5 because of the Roman numeral for V. That's not why it's in group 5, but you understand what I mean. So let's have a look at, they have a nice figure somewhere. Oh, here? Yeah, they have a nice figure here, which I'm going to zoom in on, which shows you the, I have to go to the scroll bar at the bottom. Yeah, which shows you the arrangement of electrons in those outermost orbitals. So many of you may know that in a transition metal, when we have these particular environments, like an octahedral environment or a tetrahedral environment, the outermost orbitals, the d orbitals, the outermost filled orbitals, the d orbitals, don't stay the same energy. They are influenced by the geometry, the octahedral or tetrahedral environment, and they split into two or more different degenerate sets of orbitals. So, for example, in a tetrahedral environment, you get the d orbitals. In a regular tetrahedral environment, you get the d orbitals splitting into what's called T2, that's just a symmetry label, and E, which is another symmetry label. There's 2 E symmetry orbitals and there's 3 T2 symmetry orbitals. In octahedron, a regular octahedron, you get a slightly different splitting. You still get 3 and 2, except now they have slightly different names. It's called TGG and EG, and those are now the triply degenerate orbitals. The 3 TGG orbitals are lower in energy, and the EG orbitals are higher in energy. Okay, this is many of you may know this if you studied undergraduate chemistry. Now the question is, how do the electrons arrange themselves in these orbitals? And that's basically the whole point of this paper. How do the electrons arrange themselves in these orbitals? Because they have different choices. They can occupy different orbitals, and the different choices they make are anisotropic. They are the electrons are pointing in different directions depending on which orbitals they are in. So they kind of break the symmetry of the site, because they adopt, or they can adopt orbitals, occupation of orbitals which has less symmetry than the site they're on. So the tetrahedral site, the Fe2+, as we said before, has 6 electrons. So each electron is represented here by a rather large arrow, and a full arrow as well, not a half arrow. That's a controversial choice. So the 6 electrons here, 1, 2, 3, 4, 5, 6. Tetrahedral metal is pretty much always high spin, so that means that we fill up the Eg orbitals first, and then instead of pairing the electrons in Eg, we go fill up the TGG, the T2 orbitals. So we fill up 1, 2, 3, 4, 5. Then the last electron has to come down into the Eg, but there's 2 choices for where that electron can go in the Eg, because there's 2 degenerate Eg orbitals. So this electron can be in either one of these. This red electron has a choice in life about where it wants to go. Likewise, let's think about the vanadium 3+. Now the vanadium 3+ is an octahedral site, and it has 2d electrons, so they go in the TGG orbitals, but like the red electrons here, they have a choice about where they want to go. Do they want to be, there's 3 different orbitals and there's 2 electrons. So 3 orbitals, 2 electrons, we have some choice about where those electrons can now go into the different TGG orbitals. So where do they go? That's basically what this paper is trying to find out, using this kind of diffraction method that we talked about before. So let's zoom out and go back to where we were in the paper. Yes, so the formal charge there, we have 3d6 and 3d2, and they talked about the S2 spin state of the Fe site. It's a S equals 2 state on the, is that what they meant? Did they mean that? The S equals 2, oh yeah, okay, it's big S, okay, I think so. S equals 2 spin state of the iron site, and S equals 1 spin state of the vanadium site. It's determined by the magnetization experiment. Oh yeah, of course that makes sense. So the total spin on the iron site is 1, 2, 3, 4, 5 minus 1, but they're all half spins, so that's 2 spins altogether, whereas the vanadium site has a spin of 1, which just means those electrons are spinning parallel to each other. And that's determined by a magnetization experiment in that paper. I believe you, I'm not going to go look it up. The unit cell consists of 3D structure of 8 FeO4 tetrahedra and 16 VO6 octahedra, figure 1a. We already looked at the structure, we're not going to go back. This system has 3 structural phase transitions. Okay, well, we know that, he already told us that before, but we're really interested in this cubic one, which is the high temperature one. In the cubic phase, okay, here we go. In a cubic phase of the space group, and that's the name of the space group, FD3 bar M, because FeO4 is a regular tetrahedron, the 3d orbitals of Fe2 plus split into lower doubly degenerate e orbitals and higher triply degenerate T2 orbitals. That's what I just told you guys from this figure. Owing to the high spin configuration, and like I said, tetrahedral pretty much always high spin. Owing to high spin configuration, 5 electrons in an upspin form the half-closed shell configuration of 1 downspin electron on the orbital is responsible for the orbital degree of freedom. So the degree of freedom means it can go in 1 or 2 different orbitals wherever it wants to. Therefore, Fe2 plus has both spin and orbital degrees of freedom. In contrast, the octahedral site of VO6 has inversion symmetry, and the 3d orbitals of V3 plus are divided into lower triply degenerate T2g orbitals and higher doubly degenerate EG orbitals. If VO6 forms a regular octahedron, then the D2 electrons occupy triply degenerate T2g orbitals in a high spin configuration. Well, I mean, it's not high spin or low spin because there's only 2 electrons. You can't ever get to the point where you need to decide whether it's high spin or low spin. In a high spin configuration, okay, fine, it's also a low spin configuration if you like. And V3 plus has high spin and orbital degrees of freedom. However, the 3D state is complicated because of slight D3D distortion in the VO6 octahedron. Okay, this is the distortion we're talking about. So this is a phenomenon which happens in octahedral systems when you have unequal occupancy of degenerate orbitals, like we do here. You can get a distortion, which is normally called a Young-Teller distortion, which lifts the degeneracy of those orbitals. So you get what happens you get some distortion of the octahedron, which means that these 2 orbitals are not the same. Sorry, these 3 orbitals are not the same energy anymore. And we're going to see that in a little bit later. And they call it a D3D type distortion. D3D is just a symmetry label, a label of the lower symmetry, lower than octahedral symmetry, which the symmetry that occurs after the distortion. The triply degenerate T2G orbitals are further split into 1 orbital and 2 degenerate orbitals by the crystal field formed by the surrounding anions. Okay, so that's they kind of show a picture of it down here, I think. Yeah, so here's some possible splittings. So we won't get into the bit at the bottom yet. Here's some possible splittings of those T2G orbitals. So here it is where they're kind of degenerate. They start off here, but after the distortion they could be one of these 2 things here. So you can either have 2 orbitals go down in energy and 1 orbital goes up in energy, or 1 orbital goes down in energy and 2 orbitals go up in energy. This is the different possibilities for Young-Teller distortion in this octahedral system. So that's what they're talking about here. So one orbital wave function is uniquely described by the following formula. Because the 1-1 direction is the quantum axis, okay, and then they go on to write some equations for these different possible wave functions, which are called psi1, psi2 and psi3, which are just the wave functions after the distortion of after the Young-Teller distortion. Okay, so that's what can happen after you distort that VO6 octahedron, as we saw in the structure that we looked at a minute ago. Okay, let's have a look at what they did here. So look at the actual results. Excited experiments were performed using single crystals. Let's go to the excited experiments using single crystals on this beamline at the synchrotron facility in Spring 8 in Japan. We went through how they did it on the previous paper, so we're not going to jump to that now. Figure 2D and 4B show the observed valence electron distribution around the vanadium. Whoa, too much. I don't even know if I can undo that now. How do I get rid of this? I think I've highlighted everything forever. Okay, let's go back to the pen. Around the vanadium half position and the iron 1/8 position. So that's just particular positions in the unit cell at 160 Kelvin. The valence electron density around the vanadium site is more clearly anisotropic than the iron site, The reason is only 1/6 of the d electrons in iron contribute to the anisotropy. So if you look up here, these electrons are all isotropic, but you only have one of the electrons out of 6 has this possibility for this anisotropy. It's different orbitals that it can occupy here. Whereas in the vanadium site, both of the electrons can contribute to the anisotropy. So they're saying it's easier to see the anisotropy on the vanadium site because all of the valence electrons are anisotropic compared to iron site where most of them, where 5/6 of them are not. Okay. Yes, contribute to the anisotropy. Only 1/6 of the 3d electrons contribute to the anisotropy in the Fe site, whereas the vanadium site directly reflects the anisotropy of the 3d2 electrons. Okay, so both of the electrons contribute. The anisotropy of the valence electron density at the vanadium site was considered as follows. So again, thinking about their Yarn-Teller distorted octahedron, they have these two wave functions. They're 3 wave functions. Psi1 they defined earlier. Psi2 and Psi3 are here. And when a valence when a valence electron occupies one of those orbitals, this expression corresponds to the valence electron density. So you square the wave function, and tells you what the electron density is. That's the thing about wave functions. You square it, that gives you the probability of finding the electron or the electron density. Because the CDFS method extracts only the valence electron density, information on the phase of the orbital or wave function is not obtained. Hence, we expect the effect of orbital angular momentum L to be negligible and focus mainly on the Yarn-Teller effect. Okay, first we assume an orbital state where the energy gap of the TGG orbital is smaller than the thermal excitation energy. So remember, we have this energy gap because of the Yarn-Teller effect. So that's this first case here, A, where basically the TGG orbitals are all degenerate. Then they calculate what the electron density, the valence electron density, would look like around the vanadium, and it looks like this kind of box. They then go on to calculate the let's go up and see what they do here. So first we assume the orbital state with the energy gap of the TGG is smaller than the thermal energy. In this case, the TGG orbital can be regarded as a triply degenerate, and Psi1, Psi2, Psi3 are occupied by the two 3d electrons with equal probability. The valence electron density was simulated, and it's shown in figure 2a. It's this one here. Yeah. They then go on to talk about 2 different possibilities where the the orbitals are not degenerate. So where you have this splitting, this large splitting, larger than the thermal energy, due to Yarn-Teller distortion. And these are 2 possibilities, and they calculate using the same way which one of these two, the valence electron distribution for each of these 2 possibilities. So they have this one on the left, it looks a little bit less boxy, and the one on the right kind of looks, I don't know how you would describe this, kind of 2 people hugging. I don't know. You can come up with your own description of what this looks like. They don't provide such a description in the paper as far as I know. But anyway. They then go on, so these are all simulated, so all the ones here are simulated, but what they show here is the observed or the measured using their X-ray diffraction technique, and you can see it matches up pretty well with simulation C. So this kind of shows us that it strongly suggests, I would say, that the splitting of the orbitals is as depicted in C, with one orbital becoming more stabilized with one electron in it, and then the other electron is in either of those other 2 orbitals up here. Yeah, so in either of these other orbitals. Let's let them say that in their own words, because I'm sure they say it in a nicer way than I did. Okay, the simulated valence electron distribution valence electron density, do not reproduce the observed electron density, figure 2d. Next we focus on the orbital state calculated by the point charge model. In a simple consideration, the 2 3d electrons form a spin singlet on a stabilized Psi1, but it does not satisfy s = 1 at the v site. In general, the energy gap of the TGG orbital due to the d3d distortion, due to that Yarn-Teller distortion, is small and Hund's rules are considered. In this case, one electron occupies the lower psi1 orbital and the other one is lifted to degenerate orbitals and occupies either psi2 or psi3. This electron configuration satisfies the need for the total spin to be 1, which means those electrons have to be spinning parallel to each other. In addition, so basically what it's saying there, the electrons are not going to pair down here. Yeah, you're not going to have this situation, yeah, where you have paired electrons down here. That's not going to happen. Yeah, because the energy gap is small, and we're going to have still follow Hund's rules. They're talking about maximum multiplicity. The other one is lifted to degenerate orbitals and occupies either psi1 or psi2 or psi3. The electron configuration satisfies the total spin. In addition, the simulated valence electron density such that the lifted electrons occupy only psi2 or psi3 orbitals did not reproduce the observed valence electron density, figure S2. We'll have to look in the SI for that, which I haven't got to hand at the moment. Therefore, we assume that the electrons in the doubly degenerate orbitals occupy both orbitals with equal probability. The simulation resulted in the valence electron density shown in figure 2c, which perfectly reproduced the experimental results. So that's what I was thinking for. So this guy here looks pretty much exactly the same as this guy here. So what they've assumed here, let me rub out this. This is misleading. Let me rub out a whole load of stuff. What they've assumed here is that the one electron goes in psi1, this lower orbital here in psi1, and the other two electrons are equally distributed or with equal probability between the two higher orbitals, between psi2 and psi3. Okay, and that's what gives you the best match. If you just put the electron in one of these orbitals, it doesn't work. That's in the SI apparently. I haven't looked at it. Or if you put it in the other orbital, it doesn't work. You have to have an equal distribution between the both of them to get this this match with the observed valence electron density. They then go on to do a similar thing with the iron. So I'm not going to go through it in a lot of detail because we've probably moving towards the end of our time we have available, and it's pretty much the same story. They look at the valence electron density on iron. It's a little bit less interesting because it's much more kind of symmetrical, because as we said, most of it is accounted for by the symmetrical, by the half shell configuration. By this half fill E and half fill T2 orbitals. The only thing to add on to that is this one electron out of the 6, which could be in give some kind of anisotropy there. They did the same thing, the valence electron density for the iron and kind of at the points of the tetrahedron, which is kind of interesting, shown in the same way. So another important point that they bring up here was that actually what they're looking at here is a time and space averaged valence electron density. So this is what they showed before on a vanadium site, which is their measured valence electron density. But this is what the experiment gives you, is a time and space average. So the experiment lasts for a long time, and it considers many millions and millions of unit cells and millions of these orbitals, and it kind of averages them all together and smushes them all together. That's one of the things about X-ray diffraction. When you're looking at an X-ray diffraction pattern, or when you're interpreting it, what you're looking at is the average structure over millions and millions of individual unit cells, of individual units. So that can be helpful. That can have challenges as well. But they're highlighting this point here, and they're actually showing that the occupancy of the psi2 and psi3, which are always orthogonal to each other, can in fact kind of precess around this, can change phase. They'll always be orthogonal to each other, but they can change phase relative to other orbitals. So they can kind of rotate around this kind of changing phase, and the average of all of these put together gives you this kind of figure here, which is what they saw experimentally. So that's quite a nice part of the paper. It kind of highlights some of the properties of X-ray diffraction that are important in crystal structure determination, but also important in this kind of understanding of orbitals. Okay, there's a bit more of the paper. They also do a little bit of inelastic X-ray scattering. I'm not going to go through that part, but I think we will have a look at the conclusions. Let's look at the conclusions. So it was found that the valence electron density with orbital degrees of freedom in Fe V2O4 maintained a state reflecting orbital anisotropy even at relatively high temperatures. By directly observing the valence electron density of the cubic phase, the orbital state can be directly determined without the need to estimate the crystal field or Hund's coupling constants due to distortion of the VO6 octahedron. We show that such orbital states are likely to be universal in high symmetry phase, and that the quantum parameters can be determined directly by simply combining them in a CDFS model, provided that the accuracy of the diffraction measurements is ensured. Understanding the electronic states with orbital degrees of freedom will provide new prospects to reveal physical properties. Okay, I think the last sentence there, I think is fully justified. I think this is a very clever way to investigate the orbital occupancy, the orbital distribution of electrons, or distribution of valence electrons within a material. Basically taking the X-ray diffraction, which comes mostly from the core electrons, subtracting the core electron part away from that, using the techniques that we saw in the original paper, and then just looking at the valence electrons. So to do that, you need to have very, very high intensity X-ray source, very high dynamic range to be able to see the very small contribution of the valence electrons to the overall diffraction pattern. But they're able to do this at the spring 8 beamline where they're working. And you know, this is an electron. I mean, this is as close as you're going to get, I think, to a picture of what an electron looks like, or what electrons look like. You know, this is kind of as near as we can get. So the fact that they can then couple this actual physical picture, you know, of the spatial extent of an electron or a pair of electrons, and interpret that successfully as they have done in terms of the occupancy of orbitals, I think is pretty phenomenal. I think that is quite a remarkable achievement, I think, to be able to do that. I think there's loads of places that this could go. There's lots of things that you could do with this. Correlation of this with computational results. You know, so many systems with, I mean, what if you did this in superconductors? What would that even look like if you could look at a material in a superconducting state and directly visualize the electrons which are doing the superconductivity? I don't know. That sounds, using this method, that sounds pretty remarkable. Loads of other things, you know, lots of really interesting electronic systems where that could be, where this kind of technique I think would be really useful and complementary to all of the other methods. I mentioned a whole load of other methods at the beginning that we have for understanding electrons, photoemission spectroscopy, lots of other different kinds of spectroscopy, computational methods. All of these could be kind of brought together, I think. I think the challenge for these guys is that as far as I know, this is the only group that does this in the world. The original paper, I think, it came out in 2020. I think it's only got 3 or 4 citations, which I think might all be from the same group. So what that maybe suggests is that this method is very, very difficult. This is not a technically easy measurement to do. You have to know exactly what you're doing to be able to get this data just right. So that's the thing that maybe will hold this back. That maybe if there's only a few groups, a few institutions, a few facilities in the world where you can actually do it, you know, that makes it harder to become a mass appeal. But for answering, you know, very specific questions, very deep questions, maybe on certain materials, this could be you know, an exceptional new technique. That is my view. That's my view anyway. You guys can feel free to disagree. You know, you may think that this is maybe not adding too much from what we already know, but there's different points of view there. I thought this was a really nice piece of work, really smart science, potentially important applications, potentially very important applications if you can find the right material to look at. I think we're going to wrap up there, guys, for today. Thanks very much for being part of the stream. Thanks for watching. If you're watching on YouTube afterwards, come along and try and catch a live stream sometime. If you are watching, if you haven't already followed, there is a follow button down below. If you hit that, you will be notified whenever we go live. If you don't want to miss any streams, you will be kept up to date about what is going on. So if you feel like following, then please go ahead and do so. You can also check us out on Twitter. We have a Twitter account for the Journal Club, which will tweet out the papers in advance. In case you guys want to read up on them before we start talking about them. So a few days before at least, I'll tweet out what papers we're going to discuss. And of course, you can always engage with the channel while we're not live streaming by talking on the Twitter. Or you can still talk in the chat even when we're offline as well. So thanks very much, guys. We're going to bring it to an end there. Thanks for joining us today on Journal Club. Hope you found that paper interesting. I thought it was a little bit different to what we looked at before, but I think, as I said, a really interesting idea. Could be the start of something big. Who knows? Thanks for coming, guys. Great to see you all, and I will catch up with you hopefully on a future stream. See you later. Bye now.